different structures. No point to discuss mass production whatsoever. Believe me, this is a very, very fundamental science. But then all new discoveries come almost every month. One of the unexpected things was so-called structural tunability, I want to say. Initially, some people believed, let's start again. People believe that you can actually describe metamaterials through average parameters when you have many of these unit cells and very large wavelength. But in reality, it never happens, because as soon as you try to make smaller features, to go into optical wavelength, you have only a few periods per wavelength. So basically, you need to look what happens, how these elements interact. If you look at this magnetic permeability functions, which are similar to electric, but it has resonance. This is magnetic resonance there, this is dissipation. So basically, omega r, this is frequency of magnetic resonance. If you, this is microscopic derivations, different methods, but this is one of the microscopic derivations. It shows us this L sigma, some parameter here, is a kind of effective inductance. But L sigma means that we basically take into account collective response of this splitter and resonators to properties. So it doesn't mean that it's a given by single splitter and resonator. Actually, if you look at the diagram, which shows mu as a function of omega, then this is a real resonance of the whole structure. And this is resonance of the single oscillator. You see that in response from these materials, quite differently from what people believe initially, so we still can describe by average parameters. But these average parameters are not coming from single resonators. We also have influence of the collective interaction between the spring resonator. This means that if you take a simple stack of those metamaterial layers and try to shift them, we should see different responses. That's what we discovered by very simple calculations and verified in the lab, that this is a position of resonance, and this is latest shift in the periods of 1 unit, half a unit cell. Or one of the spacing period. You see that we can basically very dramatically position of resonance and basically switch from complete transmission to complete reflection by slightly shifting the layers. And this is actually surprising. This means that all metamaterials can be engineered not only from macroscopic point of view, but also from microscopic point of view. Basically, you start to stack these elements in the different rules, and we can actually get completely different parameters. We tried to check it in the lab last year. This is one of the simplest metamaterials for microwaves, splitter resonators, and composite on the boards. And now we can basically get shifts like we described here. You basically see is a shift of this magnetic resonance frequency. It's a relatively dramatic shift, and also response of the material, which we may measure, actually also reflects this fact that different shifts dramatically change the values of your resonance, values of negative index parameters. But then we found even more interesting things. If you try to actually consider the material which consists of the stacks, like I said, but every layer has a different arrangements of these splitter resonators. In one case, we have a neighboring layers having the cut here or the oppositely directed cuts there. And the other case, we have the same directions of cuts for neighboring sets. So this is metamaterials, but neighboring is just like a staggered structure of these holes. And you see that for one case, as soon as you start shift them relative to each other, we see the shift of the resonance to the right. In that case, as soon as we start shifting the layers, we see the shift of resonance to the left. So we have many developments of that. I just show you that now people realize, even Wegener tried to fabricate structures when he rotates different type of splitter resonator. People try to understand that this is not only about averaging, about macroscopic parameters. This is about engineering nature. So basically, we start from this small magnetic resonances, resonant element, and we create materials with any desired properties. This is only happening. Only happening now. So basically, I think we will converge to some of the general ideas. Now I talk about nonlinear properties, and nonlinear properties is actually what my department should be working on, because we are nonlinear physics center. So that was one of the tasks when we entered the field a long time ago. We wanted to look at nonlinear properties of materials. I mentioned that we selected a very simple way. Actually, we were one of the groups who suggested that, and we basically apply magnetic fields. We have some kind of field enhancement in the gap when this cut is made in a metallic ring. And this allows you to introduce intensity-dependent characteristics, in particular derive very explicitly effective value of magnetic momentum as a function of applied intensity of applied magnetic field. So basically, in that way, we may create nonlinear materials which will have a nonlinear magnetic response. Similar like in non-usual optics, we have a nonlinear electric response for Kerr effect. Of course, we may have also magnetic, a nonlinear dielectric response. But then, what is the idea? Why we need this nonlinear metamaterial? This is a typical dependence on magnetic permeability. I mentioned several times that this negative index is related to resonances. A resonance near specific magnetic resonant frequency. So basically, negative index in that particular region of frequencies. Now, assume that we can somehow tune material parameters. This means that if you put frequency there and our response will depend on intensity, basically intensity function somehow will be homogeneously shifted because it will depend on amplitude. I start increasing amplitude, what will happen? I'm going out of resonance. But what is that? If here I had epsilon negative and mu was negative, so epsilon mu both negative, that was metamaterial with left-handed properties. If I take our parameters or mu out of that region, epsilon still negative, mu now positive. Mu positive, epsilon negative, this is opaque material. So we have a possibility of so-called phase transition. We can, by changing in amplitude of applied field, we change material from transparent to opaque and back. That looks like interesting opportunity, and this is only valid for this type of materials. I don't comment on these papers. I just want to say that we made a lot of simulations before we actually attempted experiment. Now, this is numerics 1D showing that with applied fields, obviously because this piece of material is opaque, nothing is transmitted. But then we increase amplitude of this field. If we pass this point, we make material transparent, and there is some wave which is propagating through originally or a linear limit completely opaque material. This is for two different fields, and for two-dimensional simulations before I show experiment, this is a similar case. So we place a source there, we increase power, and basically power means that these high amplitude waves come into this interface. For high amplitudes, properties of material change, and material allows to transmit energy. And this is, before showing experiment, I want to say how we make experiment. We use initial experiment with microwaves structures, and we place a varactor diode in every split ring. So basically, all magnetic response become tunable. In average, we have nonlinear dependence response due to that fact. So for single split resonator, we can measure shift of this resonant frequency, but the whole materials look like that, the different type of structures. So basically, this structure is similar to David Smith structure, but every split resonator structure has this varactor diode, so magnetic response become nonlinear tunable. So changing the applied amplitude or apply the amplitude of applied waves, we can actually change parameters of the structure. I come now to experiments. So this is for, again, for structure. You see that there is a dependence on the intensity of applied field. of this resonance. This is already a resonance of the whole structure, not a single resonator, because it's much more complicated than a single sharp, nice resonance. And basically, if you fix frequency somewhere there and increase power, we see that there is actually here. So, but of course, you should realize that it's extremely lossy structures. So basically, we have a change of transmission, but at least 30 dB. That's what we actually realize in experiment. Now, what we have a material, and we have a source. Material is like a slab of this composed of the splitter and resonators, and each of them can be tunable. So what we see initially, this material is in opaque region, mu is positive. Then we apply the source and increase power of the source. When increase power of the source, high intensity wave change properties of these materials, it shift resonance to the region of transmission. So basically we see enhanced transmission. So here, so if the blue, so green somewhere there, so we have dramatic change to red, so about 30, 40 dB change of transmission with the increase of power. Then another experiment, we have completely transparent. We select frequency, which is exactly in the transparent region when we have a negative index. Then we see that this is a field measured just behind of the slab. And then we increase power, we shift the operational frequency out of the region where we have negative mu, and you see that basically this material becomes completely opaque, it doesn't transmit much as used to transmit. So this is all microwave experiment. Of course, all tunability, people try to get to optical domains, so there are many interesting properties for second harmonic, third harmonic, fourth harmonic generation. This for this metamaterials based on varactor diodes, this is a much stronger effect than was first reported for optical metamaterials or terahertz metamaterials, because these are not phase matched processes with very strong response due to this varactor diodes, highly nonlinear device that can be all measured. Also, this varactor diodes can be used to tune different types of structures. This is one of the structures, so-called epsilon near zero channel, which combines two type of materials to region where epsilon almost vanishes. This allows to make a matching, for example, waveguides, and of course there's a kind of resonance effect. And now if you introduce this varactor diode, we can also tune this matching resonance in the way which we did tunability of usual metamaterials. So there are many types of applications, and people may wish to expand all these applications, but of course the main goal of majority of groups to make it operational for optical wavelength and get a tunability. But so far we need to find analogs of this magnetic resonance, tunable magnetic resonances in optical domain. At the end of my talk, I come to a few problems which are associated with so-called plasmonic and plasmonic devices. I selected that because there are interesting lessons to learn which not actually appear in textbooks from all these plasmonic activities. You know that plasmonics is a very active field, particularly for those who want to marry optics and electronics, because these are waves which exist in the interface between metals and dielectrics. We involved electrons excited in metals, so it's electromagnetic surface waves. And people, because of metals with high and negative epsilon, we have a very strong localization, or sometimes called subwavelength localization of these waves. And people study different types of modes, waves, propagation, etc., specifically for this surface plasmon polariton. Of course, the main idea to find applications, so they are very nice tunable sensors. Also, people believe there are plasmonic circuits, signal processings, and some components of integrated optics where optics and electronic can be superimposed. If you open literature in optics, you see many papers on plasmonics, very hot topic. And then if you go to analysis, not that much done analytically, because there are TM modes, particularly for nonlinear systems, obviously there are strong losses from metals, and many of the simple theoretical approximations just not valid there. But we're interested in nonlinear effects. I will mention a few of them at the end. But first of all, I want to mention the very special things about this plasmonic type of waveguides. In optics, we have modes of two kinds. We have propagating modes and evanescent modes. That's already I mentioned. But optics usually lossless. We don't have losses in optics because they're very small, everybody ignores them. Then the typical analysis of waveguide modes or any type of modes of optical system is the following. You assume that you don't have losses. When you don't have losses, you study your system to find guided waves or waveguide modes. You find modes. These are modes which are guided in that sense that they are propagating along waveguides and decaying outside the waveguide. Then if you want to include, basically you have all classification of modes, and if you want to include dissipation, you just include dissipation by perturbation theory. That's basically how everybody described optic system. Plasmonics have metals involved. Metals are very lossy materials. So basically from the very beginning, in metals we have strong losses. This means that our propagation constant, beta here, neither real nor imaginary. It's almost complex. So all modes in plasmonics were evanescent modes because they decay eventually due to dissipation. Now the question is, what would be right behavior with the study of plasmonic devices? And that's what we actually found from our analysis. It's not explicitly written in textbooks. Let's take a simple example. This is a metal, dielectric metal. This is a mode which is this waveguide called slot waveguides because we have slot between two metals. And we study modes of this waveguide similar to waveguide based on metamaterials. We have a symmetric, antisymmetric mode. This is a branch of symmetric modes which approaches plasmonic frequency, and it consists of two surface waves. So each of them, this is surface waves, surface plasmon polyritones, surface localized at the interface between metal and dielectric. So guided modes are just a pair of these surface modes. Now, this is a dispersion without losses, and that was done for many years. However, what happens if I just add slight losses to the system? And this is a lesson we learned. In addition to this original guided modes, we have evanescent mode in the original lossless system. These evanescent modes are shown by dashed line. And when I add dissipation, all modes mixed up. How this happens, I come to that slide. I don't have that, okay. So basically, if I take very small losses, what I first see, that there is kind of what they call reconnections through infinity between the normal propagating modes and evanescent modes, and modes of the lossy waveguide now combine of two branches. This is former evanescent mode, and this is former propagating modes. So evanescent and propagating modes all mixed up. So we can't apply perturbation theory. Now I increase gamma, so gamma 1 is my realistic losses of metal. And this is gamma 0, is no losses. You see what happens for this intermediate state. You come to the well-known characteristics of these slot waveguides. So these are two branches, one and second one. But if you now forget about the intermediate step, and this is for imaginary part. Imaginary normal mode had no imaginary part, and this is evanescent modes, how reconnection occurs. So if you compare that plot and that plot, it's very hard to guess that these modes of realistic structure has something to do with modes of imaginary structure, lossless structure. Why? Because part of these modes originate from propagating modes and part originate from evanescent modes. This basically, of course, completeness is right. If I discuss everything in modes in terms of how many modes, these theorems of completeness, that should be all right, nothing changed, basically, number of modes the same. But in terms of structure and dispersion which are involved there, picture completely different. Now, if I see what happened there, you see that this is red, this is propagating mode, this is asymmetric mode now. It has another, this is another scenario of creation of these modes. This is antisymmetric modes. And then there is evanescent modes which actually start there. And as soon as they include dissipation, there is degeneracy of these bifurcations and basically split in two modes. It will be shown in the next picture. But this is a realistic structure. You see, it has nothing to do with the original modes. Now, another example, this is higher order mode of the circular metallic waveguide with 4 maxima. It has this dispersion relations when you ignore losses. And now I include very small losses. In fact, I should remember that there is evanescent modes coming there, red, it just comes to bifurcation point 0. If I include small losses, there is a splitting of that bifurcation point to 2 branches. These 2 branches are actually different due to the position of location, somehow rotated maximum. But in fact, they originate and create these 2 different type of modes which people may analyze here. So what I want to say is that in addition to all these problems which we have with metamaterials, we even don't know how to analyze them, because the whole guided wave theory was based on the fact that losses are 0. Then all losses include optical fibers, basically. Nobody was about losses. The losses are included like perturbation to calculate efficiency, but still losses are so small that they don't produce dramatic changes to the system. Here, losses produce dramatic changes, basically dispersion of realistic structures, very different from dispersion of lossless structures. That's the message which I wanted to deliver. So now we work a bit on nonlinear plasmonics. This is a very interesting topic as well. This is surface plasmon polariton. It's FTDD simulations which show propagation of this surface plasmon polariton at the interface between silver and nonlinear dielectric. So basically what happens if I launch that beam of finite size, of course it decays due to dissipation, even silver is a good metal with small losses. But then if a beam was finite width, we try to spread transversally. What usually happens, this is a relatively initial narrow beam which spreads and diffracts. So I believe Martin de Sterke, who has lectured after me, will talk about nonlinear quadratic and cubic effect. This is a typical behavior of a linear wave packet, of linear beam which spreads or diffract and do not propagate as self-trapped beams. But now we want to include nonlinearity and create so-called soliton. Soliton is a localized beam. And here, basically in a very lossy systems, we can't do that because losses are so strong that we can't balance losses by any nonlinear effects. That's why we don't have yet devices which will operate with plasmons as with normal photons, because the wavelength, I mean, this effective loss length, whatever, much smaller than the length of operational devices and everything expected by losses. However, the recent developments of plasmonics, I just touched on a few important topics, associated with so-called tapers. Idea of tapers was suggested a few years ago by Mark Stockman, who actually considered it tapered structure and shown that we can get effective amplifications of plasmons. How does it work? This is, I don't discuss much of this equation, I will show you only simple pictures. Basically, this is a taper. If taper selected, this angle of taper selected in some clever way, basically what we see is that instead of the decay in amplitude, if anyway propagate from straight waveguide or not very strong taper, basically amplitude is decayed. But taper can actually change amplitude of the wave or propagating inside, and basically we can almost compensate for losses or even can over amplify the wave or plasmon which propagates inside of the taper. That's quite an exciting discovery, because in that way, even the total energy is dissipating, we can still have amplitude growing, and if amplitude growing, we can get advantage of nonlinear effects. I don't know if Martin will show you equations, but this is a nonlinear Schrödinger equation I don't discuss, and the tapering enters with this linear term, which actually compensates. This is taper functions, and this is losses, so you see the taper functions can immediately affect straight losses in this tapering waveguide. Now, of course, we can basically play with the solitons in nanotapering, with this nanotapering, this basically compensated beam decay to stable propagations, or even this amplifying theory. This is also FTDD, but for different transverse directions. I'm coming to the end. Why do we need all these metamaterials? I don't know if Ross emphasized that at the end, but I believe I need to emphasize because you come from different fields. First of all, unexpectedly, we found an area where there were many interesting fundamental issues. I didn't mention even in part of them. For example, with Ross and his colleagues, we collaborate on so-called Anderson localization. Anderson localization, this is effect of localization of wave functions well known in solid-state physics. Of course, there is analog in optics of Anderson localization. As soon as you introduce that in materials, rules of localization change. So this is what I try to say. This is a source of new fundamental questions when you change sign of mu. So that's interesting because we can still find unsolved and very non-trivial problems. That's issue, particularly for younger people. Then, interesting for me, for example, it's linked to many other fields. It's linked to not only for guided wave optics, but also to plasmonics, to imaging, to different type of links immediately developed, or just knowledge of composite materials is very broad, and actually as a part of different developments, and we have properties of different type materials ranging from simple metals to dielectrics. This link I mentioned, that of course for us it was very important that we were able to start microwave experiments at relatively cheap. It doesn't require a lot of money. Of course we are now able to do much more, but initially that was important. And still we have a lot of promises in application in optics, but again, mass productions that will be important components to compete with any kind of telecom. Now with schools we face that question because people ask, okay, you made something good, but how much it costs? That's an important issue. But for younger people, it's very important that a lot of media relations and a lot of hype. For example, our experience was interesting. As soon as we started to work on metamaterials, but never mentioned invisibility or cloaking. And in one stage, we mentioned that, and it was in our university, physics-wise, presented by one of our guys who write about science, that, oh, these materials, what they're useful for, invisibility. So this is interesting property. And then it was a university media release. Next day we got like 20 calls from different newspapers. So then I was not in the university, but then what we wrote, Australian joint race for invisibility. And then immediately, who else? Harry Potter, you know. So if you're after all this media releases, that's probably the right way to do, because people are still attracted by all this curiosity, you know, like invisibility or other things. I stop here. I take your questions. Thanks a lot for your attention.
Just point out, there's one interesting thing you didn't mention, but with the physics that comes in from strong loss, there's no analogy with electron physics, because in electron physics, when you have that much loss, the electron beam is completely gone. So photons are much more resilient to loss than electrons. So.
But electrons, we still write like kinetic equations and produce some kind of...
Yeah, but no circuit in electronics will tolerate the kind of loss that we actually put up with, and optical circuits still work. Okay, questions from the floor, please.
Nobody wants to work on metamaterials.
Who wants to work on metamaterials? Have got the new champions?
Yes.
You were talking about you were able to enhance the propagation of plasmonics using sabers. How much are you able to enhance this length with nonlinear results?
There are many different issues. For example, how we should taper. So people are still studying that, and you have papers which studying how we should do it. We should do it adiabatically, or we should do it. Of course, in theory, if you ignore reflection, you take a big taper and you get what you want. But of course, in reality, it's not. So tapering should be close to adiabatic, not exactly adiabatic. And then interesting things which we just got paper accepted on a very trivial issue. We ask ourselves simple questions. I don't know why nobody asked before. What should be tapering profile to compensate losses exactly? The answer is not a linear function. It's much more complicated function with minimum. So even this one, because taper change many parameters, change field parameters and also material parameters. So it's more complicated dependence. So even this one is not yet understood. But tapers is the right way to go to actually amplify the amplitude. But you can't completely beat losses. So beating losses means that amplitude is growing, but total dissipation, of course, if you write it for total power, of course, it will be always decreasing because of losses. But you somehow manage to concentrate field and get amplitude amplified. But so tapers, usually it's about a few degrees, already very efficient to enhance amplitude 2-3 times. And then papers are coming. This is very hot topic. Hot topic, nanofocusing. Even nanofocusing was adopted for nanofibers. When you take optical fibers and create a nanofibers, very thin fibers, and then this taper also can be used to amplification. Actually came a bit later from Plasmonics, but it's again very hot topic. Nanofocusing.
In your fundamental issues, there is an interesting one I became aware of just recently, and that is in electromagnetism, when you have corners, you have field concentrations.
Oh yeah.
But when you do it with metamaterials, it's actually still a research question as to how strong a field concentration you should allow, and whether a metamaterial corner can actually radiate.
Because you don't have fundamental mode. You don't have mode which can be concentrated. You sit on the two surface plates. So I guess you got the feeling that it's not a Finnish direction. So it's everything is developing as many other subjects, right? But what is really fascinating, how all the subjects are linked together.
Yes, it's an area where all the problems are hidden and hiding is the problem. Okay. Further question, please. Yes.
Those spirals that you were showing, what they are made of? The spiral metamaterials?
Chiral, it's a spiral.
Yeah.
It's done by optical two-photon absorption laser writing. So basically, it's done from specific type of polymers. But then, of course, what you can do, you create like a platform and you can put different materials, or you can dope them with different materials. But originally, it's done from polymer.
So there is no metal in there?
No.
No metal?
No metal there.
So,
But you can put metal there, yeah.
so are they done from polymers that they will not be so lossy?
Of course, polymers are not lossy, but because of the coupling of magnetic and electric field, you can still have interesting effects. Now actively people discuss diodes. So it's optical analog of diode. You have transmission one way, another transmission. And here exactly, when you have spiral structure, you have right or like circular polarized or linear polarized light. Transmission will be different depending on it's left or right polarized, so in which side you enter.
We actually haven't mentioned it today, but one of the ways you can think about manipulating light is through polarization, and that's probably one of the neglected areas of metamaterials, which we expect to see rapid developments on in future years, because actual control of polarization, you can place information in the polarization of light as well as in its intensity.
But in metamaterials, not much studied.
No, it's just a field which is
very good.
What were the sizes of those spirals? How big they are?
I don't remember, but you can easily check it.
They micrometers or nanometers scale?
No, not nanometers, micrometers.
Yeah. Yes?
One more question. It's about the taped material. You just mentioned the taped material is what kind of material you use?
No, it can be done like a groove in the metal. You know, you take a metal surface, you just create kind of that.
How much the size?
Even size inside, 50, 60, 100 nanometers. That's actually for plasmonics. This is normal scales for this plasmonic waveguides. About 100 nanometers.
Yeah.
Maybe you use the taped fiber and when you coat it.
No, fiber is a different story. It's a different story. Why? Because here it's very nice because we have metal. Metal has a large, even negative epsilon. If you have a large epsilon, we have a big jump of epsilon between core and cladded. This means we can get wave localized strongly, so sub-wavelength localization. Fiber has a very tiny refractive index, so refractive index differs from air by a small amount. This means that as soon as I try to taper dielectric waveguide, not metal waveguide, your wave spreads, so you need to taper like a silicone type of waveguides in order to get higher refractive index. Otherwise, you will lose all energy, so it will not stay in the taper. So fiber tapers are used, but not for this one. They are useful for resonances, for example, or for sensors, because we have a big area of evanescent field.
It's interesting, I mentioned the spacer at the end of my talk, and one of the concepts, the first concept of the spacer was actually to use that taper.
Yeah, that's correct. So from Max Stockman.
Yeah. So the actual realizations are somewhat different from that, but I think the taper idea is still a very interesting one.
At this stage, I think that it's probably the only idea to get really nonlinear effects working. Otherwise, you need kind of amplification, effective amplification of amplitude.
Yeah. Okay, further questions, please?
People want coffee, no?
You want coffee? All right. Okay, well, let us thank Yuri. 3:30, we resume for math and the
Where's Raul? Where's Raul?
We work with Iman.
Now I understand your question.
Yeah. I guess we're using liquid crystals to self-assemble nanoparticles. In the structures.
No, but this is a completely different approach.
It's still very fun. We're
Yeah, yeah, it's
just
You are going to close your lecture? You can close.
So you know about the Dampo nanorods that Shalai
Three-dimensional, you mean that
You need the
well,
bulk.
stuck like that, stuck like that.
Yeah, so, you know, we just had a paper retrospect where we have a millimeter 6 sample, and it is around 100 volts and 1 volt.
Okay.
Right, so it's 3 pieces.
But they're not pairs.
They are not yet.
But what do we see?
Well,
What do you change?
we saw just polarization dependent surface plot resonance. Those
Turn it off.
Okay, so you have magnetic resonance.
Yeah.